We left off talking about this diagram, which illustrates a number of geomorphological features that are generated by glaciers. Starting at the top, the head of the glacier, we have the head wall. So this is the actual starting point of the glacier, its highest elevation. Adjacent to this head wall is what is called the bergschrund. Bergschrund means mountain crevasse or mountain crevasse, and it's a crack in the ice that forms from the surface down to the bedrock. So this is a major impediment to any climbers that want to make it to these ledges here above the glacier. A horn is just that. It's a horn-shaped rock that's generated by glacial activity. We'll take a look at the world's most famous horn in a minute. This is the area where snow becomes firn, and firn becomes granules, and the granules eventually become glacial ice. So it's the area of accumulation. Now beneath this, we have bedrock that is fractured physically by freezing and thawing cycles. This bedrock can be plucked or embedded in the base of the glacier and then dragged down the slope across the surface of the bedrock, eroding the bedrock and at the same time modifying the grains, rounding off, breaking off the edges, smoothing the surface, and decreasing the size. So this material can be dragged all the way down or drug all the way down the mountain from the head wall to the terminus here, where it might be deposited as till in the terminal moraine. Along the way, we pass a tributary glacier. This is going to form in a depression in a mountain off to the side of this main glacier. Ultimately, this ice is going to flow down slope and join this main glacier as a tributary glacier. And as a result of this, we're going to develop a medial moraine, a pile of loose debris that is located between the two flows, the flow of the tributary glacier and the flow of the main glacier here. On the sides of the glacier, we form what are called lateral moraines. This is a combination of material in the ice and material that falls off the slope here onto the surface of the ice. If the cirque is to become ice-free and filled with water, we call that a tarn. So this cirque is known as a cirque in French. It's a corrie in Scottish. It's a coombe in Welsh. Adjacent to this cirque, we may have an arrete. An arrete is a French word for knife blade, and this indeed looks like a serrated knife blade. So there would be another glacier just on the other side of this arrete. So the combination of two or more glaciers will give you this knife edge geomorphological feature. If the glacier is to retreat, become smaller, and that's what's happened here, then we're left with what's called a hanging valley. So if this glacier was to go away, to ablate completely, there would be a hanging valley here. So this is a previous glacier during colder periods. Now, if we make it all the way to the end of the glacier here, this material is relatively unsorted by this transportation. It's going to reach what's called an outwash plane. And at this point, flowing water over the material will do some sorting. So there may be some imbrication of grains and some general size sorting, accompanied by the movement or transportation of this till away from its depositional site to a lower elevation. Some examples of what we just talked about. This is a bergschrund. Again, it's a crevasse located right near the head wall, and it's going to extend all the way to bedrock. So these often fill with material during the winter, the material being snow and ice, either is in the form of avalanches or simply snowfall that drops down into this. And we may cover this crevasse with a thin snow bridge that you would potentially fall through when traversing this glacier. So these are dangerous features. The world's most famous horn is the Matterhorn, and it's located in Switzerland. Lots of cool villages around here. You can sit and drink a cappuccino or an espresso or a beer and watch people climb these faces. It's back in the 70s. There was a band, Jethro Tull. They started in 62 and they're still active today, just put another album out. They wrote a song about climate change, and this is one of the songs about climate change called Something's on the Move. which caught my eye early on because I didn't know what this word meant. I saw corrie. What the heck is a corrie, and why is this thing pausing there? Turns out the corrie, again, is a Scottish term for cirque, which is a French term for coom, which is the Welsh term for the same thing. So we see this is actually a song about glaciation, which is kind of cool. And you can listen to the song here. Okay, other features that we'll observe in glaciated areas include glacial grooves and striations. So that's seen here on Kelley's Island in western Lake Erie. So what happened here was boulders and gravel and cobbles and other bits and pieces of rock were embedded in the base of the glacier coming out of Canada and pushed over Kelley's Island towards Ohio, which is now, it is Ohio now. So this material is pushed south, and in doing so, it's dragging those boulders along the surface of the bedrock, grinding into them, much like a belt sander would grind down through wood or concrete. This is a photo of an arrete, which shows clearly the knife edge look to this geomorphological feature. Again, there would have been a glacier here in the past, eroding all the way up to this surface, and on the other side, another glacier eroding the back side of this face here. Now, material can be transported by glaciers in a couple different ways. Material can fall on the top of the glacier. This is called supraglacial debris. This is going to accumulate on the surface. Basically, after rolling down the slope or sliding down the slope onto the top of the ice here, which you can't see because there's so much debris on top of it. Okay, so glaciers can carry debris on the top of them. Meanwhile, at the base of the glacier, basal debris gets entrained by the processes of abrasion and plucking from the bedrock below. This material gets pulled up into the ice, it's entrained, and it's dragged along the bottom, grinding against the bedrock. Supraglacial debris is dominantly coarse-grained material with a low proportion of fine-grained sediment, whereas the basal debris has a wider range of grain sizes that include fine-grained rock flour produced by the abrasion processes. Basal debris of fine-grained to coarse material tends to be most abundant in polythermal glaciers because the alteration of pressure melting and freezing of the ice in contact with the bedrock exerts a strong freeze-thaw weathering effect. So it's very aggressive at breaking up this rock with this daily freeze-thaw cycling. As glaciers move down slope, they twist and turn and deform, moving around and over objects, sometimes grabbing onto those objects and carrying them along with them. So at the base of the glacier, we're going to mix this basal material with some supraglacial debris that falls onto the top of the glacier. So that gets stirred up. And additionally, when two or more glaciers come together, we're going to see the development of a medial moraine in the main body of this new trunk of the glacier, this new larger trunk of the glacier. Now at the base of this glacier, the debris can be modified by grinding against bedrock, also grinding against other clasts, breaking them up, making them smaller and smoother. Water moving within channels at the base of the glacier are called englacial channels or subglacial channels. These will sort the material to some degree, but it often gets remixed subsequently. Meanwhile, supraglacial debris that stays on the top is generally unmodified. So it sits on the top of the ice as the ice moves down slope, and it will therefore retain its size and angularity. When this material is eventually dropped by the ice, we call it till if it's unconsolidated, or if we begin to cement it together, it's called a tillite. That's the rock version of till. So these terms are going to apply to a process of deposition. Here we have a cross-section of a polythermal glacier. The main body of the ice here, bedrock below, and englacial debris here within the body of the glacier. Tills can be broken into a number of different categories depending on how they originate. Melt-out tills are deposited by melting ice. As the ice goes away, the material is left behind. Lodgement tills are going to form beneath the ice by pressing debris against bedrock. These two types of till together are known as basal tills. The erosion by glaciers can generate a wide range of clast sizes, as we've discussed in the past. Laminar ice flow provides no opportunity for these different portions of the ice to mix, and therefore no material sorting occurs. Glacially transported materials, therefore, typically very poorly sorted. When we look at a till, we can see clasts of all sizes, from microscopic, which you can't see, up to boulders, the size of a classroom, school bus, or even a house. So this image is the Vatnjokull of southeastern Iceland. This is the largest ice cap on Iceland, and we can see it melting out here, generating a melt-out till. So this basal till is going to accumulate at the toe of the glacier here. Same glacier seen here from a little bit greater distance. And here we're going to see fragments plucked up by the ice as very angular blocks of basalt. Once they're entrained within this ice, they undergo no further modification. Iceland has two blue lagoons, one is cold and one is hot. This is the cold one. And again, we see the Vatnjokull in the background here, in this case, calving icebergs into this bay, into this blue lagoon. Within these blocks of ice, we can see debris entrained in the ice. So this debris most likely fell from the edges here onto the ice surface, got entrained into the ice, and as the ice calves into the blue lagoon here and melts, this material will be dropped out. So this will be coarse, fairly unmodified material that's being deposited in this basin. Because there's no chemical weathering in this cold environment, the mineral composition of the deposit will be the same as the original bedrock, which in this case is mid-ocean ridge basalt. Clay minerals require chemical weathering. Clay-sized particles don't. So one of the characteristics of glacially transported material is it imparts a blue color on water. So in the case of rock flour seen here in Moraine Lake in the Canadian Rockies, this blue color is generated by very fine particles of rock. Not clay minerals, but clay-sized particles, and very small particles, clay-sized particles of the minerals that made up the original rocks. Because these are not clay minerals, but rather clay-size fragments, they're not going to flocculate. So they stay in suspension. Now we can see a blue lake here. This is located in Manitoba. That's blue for an entirely different reason. In this case, the lake is blue because of very tiny calcite grains that are being produced by charophytes, macroalgae that we'll talk about later in the course. Now, just to be extra nitpicky, material carried by glaciers is not necessarily the result of glacial erosion. In this image, we can see the valley walls are quite steep, and freeze-thaw cycling is going to generate loose material that falls down the slope onto the top of the glacier. And at this point, in temperate regions, detritus might also be washed down these valley sides during the spring melt, summer thaw, as this ice here and further up the slope melts and drains down into the valley. Modern landscapes that have been covered by quaternary ice sheets show us a wide variety of depositional landforms. These characteristics provide us with information about the glacial processes over the last few tens of thousands of years, and also give us an understanding of the origin of the landscapes around us. Most continental glacial deposits, though, are unlikely to be preserved in the stratigraphic record. So they're ephemeral features. We generate them during glaciation, and then we begin to destroy them as soon as the glacial episode comes to an end. Many of our modern glacial landscapes, therefore, are undergoing erosion. Over time, these will be reworked and removed, so essentially erasing the glacial record as time goes on. These are very seldom preserved. Moraines can be subdivided into a couple different types. These are accumulations of till that form at the margins of a glacier. We name these moraines based on where they're located relative to the glacier. So terminal and end moraines mark the limit of glacial advance, usually a ridge of gravel that stretches across a valley. Push moraines are formed when the glacier acts like a bulldozer, essentially shoving material along the ground in front of it. And eventually, as this ice melts, backs off, this will be left behind as a moraine, as we see here. Dump moraines form at the snout of a glacier where the melting ice keeps pace with the glacial advance. So we think of it, this is kind of a conveyor belt where material is being conveyed to the toe of the glacier and gets dropped out. More material comes in behind and keeps this dump going. Lateral moraines, on the other hand, form ridges along the sides of a glaciated valley. So there's going to be a lateral moraine here, and a lateral moraine here. As these glaciers come together, they form a medial moraine in between the two ice flows. Now, another effect that supraglacial debris has on a glacier is that it serves as an insulating blanket. So where we see ice that's covered with rocky debris, it melts more slowly than ice that is directly open to the atmosphere, where it can take in incoming radiation. So this can result in some complications in the glacier's morphology. In the case of an ablation moraine, this will appear to be much larger than it really is, because most of the debris is wrapped around a core of ice. So the ice is actually taking up a significant volume that's unknown because you can't see it. Additional glacial landforms include lodgement till, we talked about a few moments ago. These occur when material is forced or pressed into the ground as the glacier moves. These lodgement tills are going to be deposited beneath the glacier that can form sheets that can be tens of meters thick or appear as irregular ridges, which we call ribbed moraines. These tills also form smooth oval-shaped mounds known as drumlins that can be tens of meters high and hundreds of meters to kilometers long. And these are going to be elongated relative to the direction of ice flow. So they kind of look like a Thule cargo box on the roof of a car. In temperate glaciers, partial melting of ice results in rivers flowing through tunnels within or beneath the ice that can carry sediment dropped by melting ice. The deposits of these rivers form ridges, snake-like ridges, that are known as eskers, and they can be a few meters to tens of meters high and tens of meters to hundreds of meters wide, and they could be as much as several kilometers long, basically covering the entire area that was formerly under the ice sheet. These deposits are gravel and sand that form cross-bedded and horizontally stratified lenses within the esker body. We can distinguish these from river deposits by the absence of associated overbank sediment and by the internal deformation when sand and gravel layers collapse as ice around the tunnel melts. So these are going to be seen as positive features that stick up above plane. Ice blocks that are embedded in this till can melt, forming kettle lakes, seen here. Now eventually, as this water moves through this region of glacial deposits, it's going to destroy these features, these deposits. Kames, on the other hand, are mounds or ridges of sediment that form by the collapse of crevasse fills. Sediment formed in lakes lying on top of the glacier or products of the collapse of the edge of a glacier. Glacial and periglacial deposits such as moraines, eskers, kames, and so on have a very poor preservation potential because they're generally destroyed by subsequent glacial episodes. Here we see the height of the last glacial, known as the late glacial maximum, with ice extending down into the southwestern United States. All of the Midwest is covered with ice, and of course all of Canada is covered by the Laurentide ice sheet and the Cordilleran ice sheet, which is located here to the west. An outwash plain is a broad, flat area formed by glacial meltwater flowing away from a glacier. These plains are typically found in front of melting glaciers and can extend from considerable distances. As a glacier or ice sheet melts, it releases very large volumes of water, along with any sediment transported by the ice. Rivers flowing away from the ice front over a broad area of the outwash plain are known by their Icelandic name, sandor. Rivers transport and deposit this material in the same way that a braided river would. So these are essentially braided rivers that are flowing out of the Vatnjokull here in southeastern or south central Iceland. So the amount of water that comes out of these can be very, very substantial. During a Jökulhlaup in the 90s, it's believed that the water pouring across this outwash plain was equivalent to all of the fresh waters flowing on Earth at that time for about a 3-week period. Now we'll take a closer look here. This is the main circle route that goes around the country, around the entire country of Iceland. And we're going to take a look at this region, and it's right about here. So we see that here. This is the outwash plain. This is the Vatnjokull in the background. So it's melting and draining into this outwash plain. And then this material is getting reworked. So again, the outburst event is known as a Vatnjokull. This Vatnjokull is caused by the activation of the volcano that lies beneath this Vatnjokull. This was formerly the one of the highlights of the highway, this long, beautiful bridge that was completely destroyed by the 1996 Vatnjokull. So this formerly was a bridge that was several kilometers in length. In cold environments, these outwash plains can lack significant vegetation. This results in the material being free to be blown around by aeolian processes, further modifying the material, making it finer grained and less angular. Some of this material, silt and clay-sized grains, may be transported very long distance by wind. This material can accumulate in thick sequences of Quaternary age loess. This loess is notable for forming steep, stable slopes. So here we see a road cut in Mississippi and another road cut here in Iowa, both in Pleistocene loess. In polar regions, areas that lie adjacent to ice masses are known as periglacial or near glacial. In these regions, the temperature is below zero for much of the year, and the ground is generally frozen, a sediment we call permafrost. Only in soil and sediment near the surface do we see water forming in the summertime. Below that, the permafrost is just that, permanent frost, and this prevents water from seeping downward. So it accumulates on the surface, often generating strange periglacial landforms like these pingos here in Tuktoyaktuk at the north end of the Mackenzie River Delta in Canada. Other features that we may see include frost wedges. As these frost wedges melt, they fill with gravel and sand. This happens repeatedly until these can be quite substantial features. In marine glacial environments where the continental ice sheets reach a shoreline, the ice can extend outward a considerable distance as an ice shelf, where the ice is not actually touching the bottom, or grounding as it's known. So some of these, like the Ross Ice Shelf, can be several 100,000 square kilometers. So the big ones in Antarctica are the Ross Ice Shelf, the Rhone Ice Shelf, the Thimble Ice Shelf, and the Amory Ice Shelf. Melting of this floating ice on an ice shelf does not add any volume to the oceans. So when these ice shelves melt or break apart, they don't increase sea level, but they do tend to hold ice back behind them. If this ice is freed up, this would definitely increase sea level. Sedimentologically, the most important aspect of this situation is the deposition of a thick till sheet at the base of the floating ice sheet, laminated mud further offshore, and occasional drop stones well away from shore, material that is coming from the melting bottoms of these icebergs. Ice shelves around Antarctica contain limited sediment because there's very little exposed rock to fall onto the surface of the ice, becoming supraglacial material. Therefore, the main source is basal debris, material that gets ground or pushed along at the base of the glacier. Ice shelves break up at the edges to form icebergs, and they melt at the base in contact with seawater. It works its way underneath the ice shelf. Ice in a marine setting also occurs where temperate valleys can flow down to sea level, as we saw in the Franz Josef Glacier in New Zealand. Now, in that situation, these tidewater glaciers contain significant amounts of sediment, both on top, supraglacial sediment, and at the base as basal debris. Sea ice is merely frozen seawater and therefore does not contain any sedimentary material except maybe some wind-blown dust, which again is going to be fairly rare in these environments. Erosional features associated with marine glaciers can be substantial. Where continental ice from an ice sheet or valley glacier reaches the shoreline of a shallow shelf, the ice may be grounded on the seafloor, touching the seafloor. Any movement of this ice will gouge or scour the seafloor, resulting in a series of grooves in the soft sediment that can be meters deep and hundreds of meters long. So we see that here as this ice sheet is moving across the surface. It is gouging into sediment. It's stripping some sediment away. It's being melted here as seawater works its way underneath the ice shelf, destabilizing it. The pinning point is the point at which the ice sheet is held back. If this pinning point is breached, then this whole ice sheet can collapse, and the result is the snow and ice held behind the ice sheet is free to move down and enter the sea, increasing sea level. Now, this meltwater at the base of the ice is going to be under considerable pressure. So all this material is sitting on top of it, squishing down onto it. And this high pressure fluid is going to seek to escape. And when it does escape, it's like a fire hose going off in this muddy substrate here. So as this fire hose waves back and forth, it's blasting out tunnel valleys. These tunnel valleys may be filled with subsequent sand and gravel from the landward side. In the case of New York, we have an exposed version of this where we see the former extent of the Laurentide ice sheet marked here by the valley head's moraine. Finger Lake sitting just behind this terminal moraine. Taking a closer look here, we can see that we have a series of linear features here to the north of the Finger Lakes, as well as a series of moraines. Now basically the situation here is the Laurentide ice sheet is retreating. As it backs up, this high pressure fluid beneath the glacier is going to be forced out. And instead of forming tunnel valley glaciers in soft marine sediment, it's cutting down through shale here. This soft rock is more easily eroded than the surrounding limestones and dolomites. So this high pressure water cuts down much like a chainsaw. So we see a cross section here of the Finger Lakes as these deeply incised valleys. Now, Seneca Lake, for example, is 618 feet deep or 190 meters deep. Keep in mind, though, that the actual cut is another 1,000 feet below this. So there's 600 feet of water plus 1,000 feet of sediment below that. And then we've got another couple hundred feet of cutting above. So this is a very significant feature that was generated by the decaying Laurentide ice sheet at the end of the last glaciation. Other features that are visible here include drumlins. So we talked about these as looking like Thule cargo boxes on the top of a car or truck. So we can see some good examples here. And the lineation of these allows glaciologists to reconstruct ice flow dynamics in great detail. So here we see how the ice flowed and produced these Finger Lakes. The terms till and tillite are used to describe unconsolidated and lithified marine glacial deposits. Sediment that's released from the bottom of an ice shelf forms till sheets that may be thick and extensive beneath a long-lived shelf. So as the longer the ice shelf is occupying the same geographic position, the longer sediment is going to accumulate, and therefore the thicker the sediment deposit could or should be. These deposits can be divided into those close to the ice front, ice-proximal glacial-marine sediments. These are typically poorly sorted dimictons with little or no stratification or other sedimentary structures. They're basically just dumped out, dumping a load of aggregate from a dump truck. And then ice-distal glacial-marine sediments that are composed predominantly of sediment released from icebergs that's going to be finer material, usually. The edges of ice shelves break up to form icebergs that can travel hundreds of kilometers out to sea. They often carry very little sediment, so they don't leave good records of their existence. Here we see one cruising down Iceberg Alley in Newfoundland. Icebergs formed at the front of tidewater glaciers might be small, but they're packed with sediment. So again, think to the Franz Josef Glacier in New Zealand. It's covered with rock, and it's also got enormous amounts of sediment embedded in its base, and it's bulldozing material along. So it's pushing lots of material into the marine environment. Now, as icebergs melt, the debris is going to be released from their base and deposited as drop stones in open marine settings if the clast is large enough. So here we have just such a clast. This is dropped into fine-grained laminated sediment in Namibia. So these drop stones can be up to a boulder in size, and they're going to look very different from the material that they drop into. So importantly, these provide us with significant evidence for past glacial episodes. Now, drop stones can result from being caught up in a root ball of vegetation, such as you can imagine a palm tree being blown over in a hurricane. If that palm tree washes out to sea with its roots containing blocks of coral or volcanic rock, then that material will be dropped out in a deep marine environment when that tree finally decays and the roots loosen up their grip. Most of what we know about ice sheets are related to the Quaternary, the last 2 million years or so of geologic time. We do know, however, that glacial deposits occur at other periods of geologic time, including the late Carboniferous and the Permian, and the Hernantian glaciation of the Ordovician. and several episodes in the Proterozoic. So ice sheets at and near the poles contain the vast majority of the ice on the planet today. Antarctic ice sheet covers almost the entire continent with a fringe of floating ice shelves, whereas much of the ice in the Arctic is sea ice in the Arctic Ocean, although Greenland hosts a significant ice sheet. Compared with these polar regions, the ice in mountain glaciers is of little significance other than as water supplies, such as here in Saskatoon. If we look at the record of Arctic ice, we can see a very substantial reduction in the coverage of Arctic ice. So compared to the 1979 to 2000 average, about a 50% reduction. Looking at it in a slightly different way, 1981 to 2010, we can see again a very significant decrease in sea ice. And this results in a change in the Earth's albedo. The Earth becomes less shiny. As the Earth becomes less shiny, it absorbs more incoming radiation. And this leads to an enhancement of the global warming that we're generating by putting greenhouse gases into the atmosphere. From evidence of glacial sediment and sedimentary rocks, we know there have been a number of glacial episodes in Earth history, and now with Emiliani's work in isotopes, we see at least 14 quaternary episodes of glaciation. We know that in the past, these episodes have been even greater. Snowball Earth, representing periods of time when the Earth was believed to be entirely ice-covered. When polar ice melts, such as the ice we have stored today, it's going to release water to the oceans, and the sea level will therefore respond by rising. So it's estimated that complete melting of the Antarctic ice sheet would result in a sea level rise of over 50 meters, whereas the Greenland ice cap or ice sheet would add 7 meters to world sea levels. Now, one last aspect of glaciology that we're concerned with here is that of isostasy or glacial rebound. So during periods of glaciation, the ice layer on continents can be miles thick, and the mass, the weight of this ice pushes down on the Earth's crust, actually depresses the crust like standing on a mattress. When the ice melts, you jump off that mattress and it rebounds. It responds by going back to its original form, and this produces a four-bulge collapse adjacent to where you were standing. So we're standing here, pushing this down, which is causing this to pivot upward. As we remove this weight, this will rise and this will fall. And we can see that here in Hudson Bay, where our current uplift rate is around 13 millimeters a year. That's a very considerable uplift rate. And the forebulge down here in southern Saskatchewan and northern Montana and North Dakota is sinking. So we're actually dropping several millimeters a year here in Saskatoon, whereas Hudson Bay is going up 13 millimeters a year. So think of this as a big seesaw or pivot point here. Glacial deposits are compositionally immature. They're usually fractured and powdered bedrock. Clay minerals are rare because there's very little chemical weathering in these cold environments. The temperature is just too low. Continental glacial deposits have relatively low preservation potential, though, in the stratigraphic record because erosion by ice is going to continuously rework that material. Erosion by ice in mountainous areas is a very important process in supplying clastic material to depositional basins. And glacial marine deposits are more commonly preserved because they're not as often reworked by subsequent glaciations. Dropstones might provide a record of periods of glaciation in the distant past, as we saw here in Namibia. This is a Proterozoic glaciation. Continental ice volumes, though, are important in controlling global sea level. Therefore, just to summarize, a history of glaciation in the past is critical for us to understand global climate change and its influence on plant and animal distribution over geologic timescales.